Welcome to Chapter 1, Lesson 8, our final lesson for Chapter 1 on interpreting graphs of functions. So starting off, some vocabulary you need to know are your intercepts. So those are points when a graph intersects an axis. So for example, this here is our graph. Our x-intercept is right here at the point -2, 0, because that's where our point is crossing the x-axis. Then here is our y at 0, +2. Your x-intercept, the y is always 0 no matter what. And for your y-intercept, your x is always 0 no matter what. So here we need to interpret our intercepts. So it says the graph shows the height y of an object as a function of time x. Identify the function as linear or nonlinear, and then estimate or interpret the intercepts. Well, our graph here doesn't make a line, so it's linear. And I'm just going to circle it to save us workspace down here. It then says to estimate and interpret the intercepts. So here, looking at this, it's the height of a launched object. So whatever this object is, when we start is our y-intercept, and where it ends over here is our x-intercept. So our y-intercept is telling us that I'm just going to write that you need to listen to me talk to know what I'm saying. You should write this out, but for me to be able to write on this iPad doesn't work out so hot. So our y-intercept says that when we start, because our time is 0 seconds, our object is already about 15 feet or meters off of the ground. So when we start, our object is 15 meters off the ground. Our x-intercept then says after 7 seconds, our object has hit the ground. So I want you to try. The graph shows the height of an object as a function of time x. Identify the function as linear or nonlinear, and then estimate and interpret the intercepts. Wow, it's hard to talk today. So, linear or nonlinear? It's a line, so it's linear. And oops, I circled totally the wrong thing last time. It was not linear, it was nonlinear, because it didn't make a line. Then we want to estimate and interpret the intercepts. So our y-intercept is here, our x-intercept is here. Our y-intercept is saying that when we started with our sample, the temperature was -5 degrees Celsius at the start. Our x-intercept is showing us that after 1 hour, the temp is 0 degrees Celsius. Here we have our line of symmetry for vocabulary, and that's the line where a graph can be cut in half and the line matches exactly on either side. So you can fold it in half and it's the same on both sides. Like your ink would match if it was like creating butterflies of paint when you were little. The line that it's going about is the line of symmetry. So for here example, our line of symmetry is at x equals 1. So here it says, an object is launched. The graph shows the height of the object as a function of time x. Describe and interpret any symmetry. So here is our line where we can fold it in half and it's the same on both sides. So our line of symmetry is x equals 3. And what's that saying is that it goes up and down the same exact way. Here in our linear equation, we want to describe and interpret any symmetry. If I were to fold this line in half anywhere, it would never match up perfectly, so there is no symmetry. Here we've got positive and negative functions. So our graph is positive when it's above the x-axis, and it's negative when it's below the x-axis. The tricky part comes in when you are writing how it is. So our positive, there are 2 different places where it's positive and only 1 place where it's negative. I'm going to look here, 1, 2, 3, 4, 5. Our x-coordinate right here is 5, and right here is 2. Sorry, and this is negative 5. So our graph is positive from negative 5 and smaller. So when our x is less than negative 5, it's going to be positive. Then from 2 and bigger, it's also positive. So when x is greater than 2, it's going to be positive. Then it's negative in between those 2 points. So you make 2 less than symbols to mean in between. Negative 5 is on your left, and 2 is on your right. Then you have increasing and decreasing. So our graph here, as you read from left to right, is decreasing until this point here. Then it shifts, and now it's increasing. I'm going to go with that points at about negative 1.5. So there's 2 places where our graph is one place where our graph is increasing and 1 place where our graph is decreasing. It's increasing from negative 1.5 and bigger. So when x is bigger than negative 1.5, it's increasing. So then when it's less than negative 1.5, it's decreasing. Your relative extrema are these 2 points here on this graph. So it's where it's either at its highest, so this is your relative max, or your lowest, your relative min, but other parts are going on forever. So like there are parts where it's way teenier and parts where it's way bigger, but your relative points are here. And this is where you use your y. So your relative maximum here is 2, and your relative minimum is negative 1, because you're using your y coordinate. Then your end behavior. That's where you're looking at your graph and going, okay, you'll have this for everything. As x is going to negative infinity, what's your y doing? As x is going to positive infinity, what's your y doing? So these things get written down every single time. Then you add in what it's doing in regards to your specific graph. So here, as x is going to negative infinity, so as it's going this way, our y is going down. So our y is going to negative infinity. Then we're going to look and go, okay, as x is going to positive infinity, what's our y doing? It's going down, so it's going to negative infinity. And that is how I would write my end behavior.